Yeah, so like Paul said, I'm Silvia. I'm a PhD student at the University of Toronto, and I'll be doing a deep dive into computing swept volumes. Now, the reason I'm doing this is my newest SIGGRAPH paper, a joint work with Noah Meigerman of Adobe Research and my advisor, Alec Jacobson of the University of Toronto and Adobe Research. This is a paper that I encourage you to check out on my website, link there. We finally managed to make it public 2 days ago, just in anticipation of this talk. So I'm really excited that I get to give this talk, and finally I can direct you to the paper. It's something we're really proud of. So let's begin by talking about what swept volumes are, and then towards the half of this talk, I'll transition to talk about how we managed to solve this problem. So let me draw you a picture. You're a member of the galactic resistance flying near the surface of a planet on a top secret mission when suddenly you come under fire. As a quick reflex, you hit the button on your cockpit that reads evasive maneuvers. The ship's computer has to identify a rock arch nearby where you may be able to take cover from the fire. Now, in a fraction of a second, the onboard computer must simulate your movement through the arch and answer one very simple but key question. Will we crash against the rock, or will we clear it if we attempt the maneuver? So one way of answering this question would be to first compute the region of space that is covered by the spaceship as it moves along its trajectory, and then check if it intersects with the rock, right? In this case, there is an intersection here in red, so the computer must immediately discard the maneuver and try something else. So that was a fairly high stakes example. So let's tone things down a little. How do we carve a pumpkin? Well, we would begin by grabbing a very spooky brush like this one. We'd move it around a couple of times. And then we'd subtract the region of space that's covered by the brush as it moves from the pumpkin to simulate its carving. Another example. We simulate a long exposure image of a ballet dancer. Now, the way to simulate this long exposure would be to compute the region of space that the dancer covers and then display it with maybe some transparency to give this long exposure effect. These are three very different applications, very different settings, one that's inspired by robotics and path planning for the spaceship, one that's inspired by sculpting or 3D modeling in the pumpkin example, and another one that's just inspired by some cinematographic application like the long exposure image. So these are all three very different applications, but they all have one thing in common, which is that to carry them out, at some point, we must compute the region of space covered by a shape along its trajectory. Now, we call this the swept volume of a shape along its trajectory. In what follows, we'll use the traditional definition of swept volume, where the trajectory is assumed to be rigid. So the shape doesn't deform along the trajectory. Instead, it only rotates and translates. And of course, you may know this already, a 3D volume is uniquely determined by its bounding surface, right? So since a surface is usually much easier to compute and lighter to represent and easier to see and lighter to store, then we'll talk about computing the surface of the swept volume, which is the same as computing the swept volume. And we'll talk about these two concepts indistinctly in the talk. Okay, so given a shape and a trajectory, how can we do this? Well, as it turns out, swept volume computation has been studied for many decades. There are many works of the 80s and 90s on computing swept volume, whose results maybe don't look as impressive to us now because they are not with interactive artistic applications in mind. They're mostly just for path planning and milling and use only very simple parametric shapes because they are very limited by their technology all the time. But even though they may not be the state of the art for the interactive applications that we have in mind right now, they're still where most of our theoretical knowledge came from. So we mustn't forget about them. Okay, so let's move on from these and think today, with today's technology, how would we do this? Let's consider the most common shape representation, which is a triangle mesh. And the simplest triangle mesh ever is made of just one triangle. So let's sweep a triangle along a rigid trajectory. Now it's easy to see that the swept volume of this triangle is bounded by 5 surfaces. the end triangle, the start triangle position, the end triangle position, and 3 ruled surfaces, 1 for each edge of the triangle. Now, a ruled surface is just a fancy name for a surface that you get when you move a segment in space. So it's by definition a ruled surface. It's just, as far as we care in this talk, it just means that it's an arbitrary curved surface. So very simple, hypothetical triangle mesh swept volume algorithm that we can think of right now would look something like this. For every triangle in the mesh, compute these bounding surfaces, so the start triangle position, the end triangle position, and the 3 ruled surfaces. And of course, once you've done that, you can think of a very complicated triangle mesh for which we're doing this. There'll be many of these surfaces that lay completely inside the swept volume, so they don't really contribute to the boundary of the swept volume, and they are like redundant, and we should prune them somehow. And most importantly, there will be some of these surfaces that crash into one another. So the surface for one triangle will crash into the surface from another triangle. So we'll need to do some extra step of resolving intersections or pruning the set of these surfaces in some way. But also, and this might be something you've already encountered in working in geometry processing, it's very hard to resolve robustly and efficiently intersections between any 2 curved surfaces. We can barely do this robustly today for flat triangle meshes, let alone for these very curved ruled surfaces that may be very complicated. So we're going to need an additional step where we do some post-processing of these surfaces. For example, we triangulate them so that we make the intersection resolving easier. Now, of course, if we do this, we're already introducing error, right? Because we're doing some approximation. We initially had ruled surfaces, but then we consider that they're triangular, flat, just so that we can resolve the intersections. Also, the way that I've stated it here, this intersection step, okay, it's not always possible because it's between flat triangles, but it would still be prohibitively costly, right? If you can think that if I have m triangles in my mesh, I generate 5m surfaces, and then I would need to check 25m square in possible intersections. So that would be prohibitively costly. Like we wouldn't be able to do this for one of our real world meshes that may have 1 million triangles, right? So you may already be thinking that computing every edge's sweep is actually very redundant. For example, if I had this very simple triangle mesh, 1 triangle, and I subdivide it so I get 3 triangles, you can see that the new edges that I introduced don't actually contribute to the surface of the swept volume. And there must be there are some heuristics that we can use when looking at the input edges and the input triangles so that we don't have to compute all of the edge sweeps, and therefore we avoid most of the expensive part of the intersection resolving step. So effectively what this means is we just add an additional pre-processing step where the set of triangles is trimmed to something that's like interesting triangles, so to speak. It's actually impossible to find only the interesting ones, but we can considerably trim it to make the intersection resolving step possible and maybe doable with enough computational time, but still very, very expensive for most applications. In fact, a lot of the related work in swept volumes, the previous work from the past 20 years, is circumventing the intersection step. So, for example, Peter et al., what they do is they generate points on these ruled surfaces, effectively creating a point cloud of the swept volume, and then they reconstruct the swept volume, forgetting about these surfaces, just keeping the point cloud and doing point cloud to surface reconstruction using standard techniques. Now, they circumvented that very expensive intersection resolving step, but they did it at the cost of adding all the approximation error related to converting from surface to point cloud and then from point cloud to triangle mesh. So it's a bit sad, but it's a way of doing it. A similar idea is by Kim et al., where the surfaces are triangulated, and then from the triangulated surface, you set up a grid and calculate signed distances from the triangulated surfaces to that grid. Since what you have is actually a triangle soup, you actually find distances and then use some volumetric flood fill to get their sign. But basically, you eventually end up with a grid of sign distances to the swept volume. Then you forget about everything you did before and just reconstruct the swept volume from the grid. Again, this is a way of avoiding the intersection, but it comes at the cost of adding 2 conversion steps with the error that they mean. So we convert from surface to sign distance and then back from sign distance to surface. Zhang et al. Also improve on this by using an octree instead of a standard regular grid, but all of the drawbacks remain the same. So having to resort to these approximations of converting from one thing to another and then back to the first thing may seem a little disappointing, right? After all, if I had just told you about swept volumes, you might have thought that it was a pretty easy thing to compute. So there's another line of works that focuses not on approximating the swept volume, but on computing it exactly. But they do it for very specific shapes or very specific trajectories. So they restrict themselves to be able to compute them exactly. So the simplest case is a linear trajectory. So imagine I move this shape without a rotation and only along a straight line. In this case, the ruled surfaces generated by the edges are flat, right? So their triangulation is trivial. So I can resolve the intersections relatively simply and get the resulting swept volume. So this is relatively easy to do, relatively fast, but of course very restrictive. If I only want to do swept volumes of linear translations, well, that's a little sad. A slightly more general set of trajectories is where each vertex is moving linearly. So imagine we have a shape at an initial position and at a final position. We're going to pretend that every vertex is moving from its initial position to its final position along a straight line. Now, this is still a very big restriction, even if it might be hard to understand just from that description. For example, anything that is rotating cannot be described in this way. So this restriction makes computing the ruled surfaces and their triangulation easier. It can be done within some guaranteed bounds. And while the intersection step is far from trivial, Campen and Cobalt precisely take this approach, and with this restriction in the trajectory, they devised a very efficient intersection handling algorithm. So this is another way of restricting the trajectory. Yet another is that of Rosignac et al., where they restrict the movement to a screw trajectory. So now the shape can rotate, but its rotation axis has to be orthogonal to the velocity at every moment in time. So that's a very specific set of trajectories. If this is the case, then we can figure out some, or Rosignac et al. Figure out some specific rules to trim the triangle set very, very efficiently, and then making the intersection resolving almost trivial. Like I said, this is the approach of Rosignac et al. In other words, sweeping a triangle mesh is a very hard problem, and we can place most existing works in a spectrum between sacrificing precision or sacrificing generality. So either we approximate the swept volume and then lose precision, but we're somewhat robust, or we manage to do the swept volume exactly, but only for some shapes and only for some trajectories. So sweeping meshes is hard. So let's forget about meshes for the rest of this talk, and instead consider the problem of sweeping an implicit surface. And I'm going to use this circle as a 2D didactic example. Now, when we say we're going to represent something implicitly, we mean instead of storing a set of vertices and a set of edges, the same information we're going to store as a function f, which is negative inside the circle and positive outside the circle. This is just a function that I could query anywhere in space, or in this 2D example, anywhere in the 2D plane, anywhere on this line. And implicitly, it's describing the same shape as the set of vertices. An example of a very common implicit shape representation is a sign distance field, which you may already know. It's a function that for each point in space, it returns the distance to the closest point in the shape's surface, which with a positive sign if it's outside and a negative sign if it's inside. That's just a sign convention. So you can imagine from now on that every time I talk about implicit representation, you can picture a sign distance field. In reality, one of the key things of our algorithm is that it is much more general than that. It can work on almost any implicit representation. So I'll just say implicit representation. But if it ever gets confusing, you can imagine that I'm talking about a sign distance field. Now, one thing that's very easy to do with implicit representation, and it's actually really hard with meshes, is Boolean operations, right? So for example, if I call the function that defines this disk f1, and I consider another shape described by another function f2, then the union of f1 and f2 is given by another function f, which just takes the minimum of f1 and f2, right? This is fairly easy to do, fairly easy to understand. Well, a swept volume is kind of a version of that, right? A swept volume of this disk is basically a union of an infinite number of shapes, which we can parameterize by some time parameter t. And then the implicit function f, which represents the swept volume, will just take the minimum of all these ft. Well, how do we calculate this minimum? A common strategy in computer science, where we have something that's continuously varying between an interval and we don't know how to deal with it, is just to discretize it, right? So instead of t changing continuously between 0 and 1, we take a time step like 0.1 and consider a discrete minimum, which will give us something like this. And we refer to this algorithm as stamping. Yes, it's better than nothing, but you can probably tell it doesn't look really good, right? Of course, that's true. It'll become better if we make the discretization finer, but it'll take, and you can probably tell, it'll take very, very, very small and many steps to make it look like the smooth swept volume that we saw before. So this doesn't look like a particularly smart or a particularly efficient algorithm, right? And that's partly the sad part of working in swept volume computation. Something you find out when you enter this field. While this stamping algorithm isn't particularly good, the robustness and generality challenges of previous works makes this naive algorithm the industry standard in some interactive applications, like relevant to us, because I was on an internship when I was working on this, Adobe Medium. So this naive algorithm is actually the state of the art in many applications because previous works are so challenged in robustness and generality. So the goal of the rest of this talk is to do better than that. And how do we do better than that? Well, to do better than that, we're going to forget that we're mathematicians and just act like economists and just speculate for a while. We don't know how to compute this minimum f, but let's forget about that and pretend we can calculate f. Let's pretend. If I could calculate f for any point in space at a fixed computational cost, so I could query it on any of these points in space. The question I have now is, where would I want to query it? Well, one option that you may have heard about, you may have done in the past, is to set up a grid, like this rectangular grid, and just query the function on every corner of the grid. I'm going to use white to mean positive function value or outside the shape, and gray to mean a negative function value or inside the shape. Now, from looking at just this, it might be hard to discern the shape of the swept volume, which, remember, looks something like this. But as we refine the grid and add more and more vertices, we can start to see the underlying shape, right? So this is a 21 by 21 vertex grid, which means that to get this admittedly not really good approximation of the swept volume, I needed 441 queries of f. However, it's easy to see that many of these queries are useless. They're superfluous, right? For example, take this grid vertex here. It's surrounded by other white vertices. It's very, very far from the boundary of the swept volume. So it's very far from the object that we're describing. So we could just remove this vertex and our understanding of the shape of this swept volume wouldn't change at all, right? Similarly, this point here is so deep inside the shape, also surrounded by only other gray vertices, far from the boundary of the swept volume, that we can also assume that the value there is going to be negative. So we could remove it without losing any information. Now, we could keep doing this, and eventually we would conclude that the only interesting vertices of the grid are those that are near the boundary of the swept volume. Just these values would be enough for us to reconstruct the boundary of the swept volume, which, as we reasoned before, would uniquely determine the swept volume. Or we can look at it as it would perfectly divide space into positive regions and negative regions, which would mean that we implicitly describe the swept volume perfectly. Most interestingly, this would only mean 100 queries of F. Now, remember, earlier we did more than 400 queries. So using only the boundary already cuts our computation time by 4. But of course, this is a very coarse grid, right? This difference will grow bigger and bigger because it's a difference between something that's linear on the grid size versus something that's quadratic on the grid size. So this sounds good, but of course, you may have already caught on to the fact that there's a very big catch to what I'm saying. I only know that these vertices end up being the interesting ones because I looked everywhere. And once I've looked everywhere, it's easy to say, in hindsight, oh, I should have just queried here. But if I was just given this grid, no more information, and some tool with which to query F, I don't know where to query, right? I don't know where the boundary is. So I can't just say, oh, to make this efficient, I will only query near the boundary, because it's by querying everywhere that I find out where the boundary is, right? So that's a bit disappointing, but we can make the problem just slightly easier. Now, imagine an oracle. Someone has given me one single grid cell that we know is interesting. So a grid cell and the values of F at the grid cell, and it turns out there are some negative values of F and some positive values of F in the corners of that grid cell. Now, because of this sign change, I know that the boundary of the swept volume must cross some edges in this cell. In particular, it must cross these edges, right? In these edges, there's a negative value in one endpoint and a positive value in the other endpoint. So there must be a 0 somewhere in the middle, which means that the boundary of the swept volume crosses those edges. So I'm going to highlight them in red and call them the interesting edges from now on. So what we can do now is we can start a queue and add all the grid cells that contain these interesting edges to the queue. We then evaluate F on these new vertices, re-identify what the interesting edges are, and so on and so on. I end up obtaining all the interesting values relative to this boundary component, right? And only those. I haven't queried anywhere else in space. I just needed that initial grid cell that I knew was interesting, and I recovered all of this efficiently. Now, if the oracle was also nice enough to give me a start point for the second boundary component, then we could also recover that. Now, in the literature, this general type of algorithm where we want to compute a shape, and to do that, we trace its boundary, is called a continuation algorithm. And hence, the title of our paper is a continuation algorithm. So to sum up, we have an idea for our algorithm already. First, we need to initialize with some oracle-given mystery grid cell that is interesting and that intersects each boundary component. And that's all we need. Once we have that, we can just trace each boundary component, hug in the boundary, like I just showed you, to recover the interesting grid values of F, and only the interesting ones, right? We didn't need to compute any of those points that are either deep inside or far away from the surface. And you may be thinking, okay, this sounds good, but who is the oracle, right? How can you make sure that you get one grid cell to begin with that intersects with each boundary component? Well, in this case, we're fortunate enough for the existence of those earlier works that introduce a lot of the theoretical knowledge on swept volume. As it turns out, this is actually a relatively easy thing to do. I won't go into detail, but basically generating candidate points that may be on the surface of the swept volume is actually fairly easy. And you can do it by looking at some geometric properties of the input surface and some geometric properties of the trajectory, specifically the relationship between the normal vector and the velocity. So for example, we could cite Martin and Stevenson as a work from the late 80s that looks into these properties and shows how to compute grid cells that intersect each boundary component. Okay, so now we have a valid algorithm. We know how to do both of these steps, but not really, right? Because this all started with me saying, let's imagine I know how to evaluate f. But in reality, we didn't know how to compute it. We just pretended, right? Because it involved this continuous minimization that we didn't know how to do. And we saw that the stamping algorithm discretized it, and that looked horrible. So we don't want to discretize the time parameter, but we didn't know how to do it otherwise. So let's think about it now. Let's take an arbitrary point in space. So for example, this green point in the middle of the swept volume. And this, on the left here, let's plot what ft looks like at the green point, right? So this is going to be the function that we want to minimize as a function of t to compute f at the green point. So we're going to plot it to see just how hard would it be as a continuous minimization problem, right? It'll look something like this. Starts by being positive because it's outside the shape. It then is negative because it is briefly inside the shape. And then it ends up being positive as the disk ends up very far away. Again, if this is confusing, you can just imagine I'm moving a sign distance field. So instead of the disk and the plus and minus signs, I just have this sign distance field, and I move it around following the trajectory of the disk. And the thing I'm plotting on the left is just the value of the sign distance field at the green point at each moment in time as I move it. Okay, let's try for a different point. Okay, that feels maybe easy to minimize. Let's try another one. Okay, then maybe that's harder or easier, I don't know. Basically, the conclusion is that this is a very simple example. It's a disk, the convex shape, perhaps the most convex of shapes, a disk. It's a very simple trajectory. It's in 2D, it's not even in 3D. And already we can have fairly diverse set of functions with several local minima and radically different shapes depending on where the point that we want to query is, right? By the way, it is vital that we do find the right global minimum, because the algorithm that we designed before relied on us always finding whether a point was positive or negative so that we could hug the boundary in our continuation algorithm. So for example, we may reach this green point as part of our algorithm, and we need to identify the right global minimum here to know that it is inside the swept volume, so great, and thus get the right interesting edge, and then continue along the boundary. If we had instead gotten the wrong local minimum, right, and we had assumed that then this must be a positive value, so this must be outside the swept volume, we would misidentify edges as being interesting, and we would miss other interesting edges and deviate ourselves from the boundary. So it's key that we find the right global minimum, which means that we're probably going to need some very elaborate global search algorithm that you may know from continuous minimization, where we look for every global minimum with maybe some heuristics to discard some searches, and then we compare the minima and we make sure that we pick the right one. And that would probably entail a very big performance hit every time we compute this f, right? Unless, and I know this is the second time I say this today. Yeah, the second time I say this today, but imagine if I had an oracle that told me all of the information about this green point. So the oracle has told me what the function ft looks like at this point. The oracle has told me what the value of f is at this point, so whether we're inside or outside. And the oracle has even told me the time at which the minimum of ft happens for the green point. So that's this moment in time that we show on the left that we're going to call t star from now on. Okay, so we have, let's assume that the oracle has given us all of that information. And let's move only slightly to a new blue point that's very close to the green one. Now, can you venture what the graph of the blue point will look like? Well, if we moved only by a little bit, then it's reasonable to assume that the graph at the blue point will be very similar, very close to the graph at the green point, right? It can't vary that much if we just move a little bit, right? What about the point at which the minimum happens, right? Well, T star for the blue point, this point here, will obviously be, since the graphs are very similar, then the time at which the minimum happens for the both graphs will be very similar. So it'll be similar to the time at which the minimum happened for the green point. So how would we say this? You know, I said a lot of things like it would be reasonable to assume and all of that. How would we say this mathematically, maybe more rigorously? If I only move in space by a little bit, T star as a scalar function of space only varies by a little bit. Well, that's obviously the definition of a continuous mapping, right? So T star is a continuous mapping. And I need to put a disclaimer here. It's actually almost everywhere continuous. And there are some considerations that we need to add to our algorithm to account for those measure zero regions when it's not continuous. I won't get into them now. They're just an addition to our algorithm. You can Control F on our paper for backtracking, and you can see what I mean, but I'm not going to get into it now. So T star is a continuous mapping. So assuming an oracle has told me all the information about the green point, if I move to the blue point, we can always use T star for the green point, which I knew, as a very good starting guess for where T star for the blue point will be. Then from there, we can do gradient descent to find T star for the blue point. We have that new information now. Then we can evaluate FT there, which by definition, since T star is wherever the global minimum happens, is just F at the blue point, right? So to conclude, what we've concluded now is that computing F, minimizing this FT for a given point in space, can be really hard and expensive, unless we've already done all the work of finding the minimum for a point which is very, very close to the one we want to explore now. I'm going to pause for effect here. Can you think of a setting where we could use this? A setting where we have information for a point that's very close, and then we move on to the next point. Well, obviously, the algorithm that I described earlier, right? We assume that the oracle has given us knowledge about one single grid cell, and then we identify the interesting edges, and we only ever moved one grid cell away at a time. So every point that we query is always very close to points that we previously queried, right? So the algorithm that we described before that served to optimize the number of times we queried F, turns out it also helps us to query F efficiently without the need to discretize the time parameter and without the need for global searches, because we can just propagate this T star value as we move on from one grid cell to the neighbor, and just transfer the T star from one point to the next, so that we can start gradient descent with a very good idea for where the global minimum will be for the new point.
Hey, Silvia, can I ask a quick question?
Yeah, of course.
What happens if my function has two minima that are like well separated and at more or less the same value, and like one kind of dips below the other? So like there's like a global jump that has to happen.
Right. So that's exactly what that's 100% what I was referring to. that happens sometimes. So yeah, I don't know if you see my cursor. I don't think I see it myself. Probably not. But
no, I don't think so.
Yeah, there are points in this trajectory, for example, where that would happen, even in this example. And what we do is basically we do this, since you asked, I'll tell you briefly what we do. We basically trace both. So when we start the continuation, we will, if one dips below the other, we will like accidentally trace the wrong minimum, right? And then we'll eventually get back to that point and trace the right minimum. And then we'll sort of self-correct. The algorithm will self-correct, and we have our queue that accounts for that and sort of updates the values. And if a point suddenly realizes that it had a wrong minimum, it tells its neighbors, hey, check that you may also be wrong, right? So this is something.
To keep around. Oh, sorry.
No, go ahead.
Yeah. do you have to keep around a list of all of the local minima in that case? Like just in case one of them dips below somewhere? Like,
no, the thing is, no, the
huh.
continuation works such that if a point has two local minima, right? Each of the, you can think of it as fronts. We have a front that's propagating one local minimum, right? If it ever crashes into another front and the other front has lower values, it'll stop, because then it was tracing a local minimum. So it's kind of,
you can like never run into a case where what you're calling a front like appears halfway in the middle of your calculation.
Can you repeat
like
that?
you like if you kind of move along your grid and for whatever reason, I'm trying to think of whether this can happen or not. I can bug you later, but
yeah, maybe.
Like
this is getting like a little bit deep in the weeds of,
no problem.
It's probably the most interesting part of the algorithm, that like we actually have this self-correction where a front may like independently realize, oh wait, I'm tracing the wrong minimum, and like update itself and become the other front and self-correct, right? So in practice, there are sometimes we briefly enter into a wrong local minimum. This is still something that's linear in the number of grid points, because it would be just like tracing like a small surface inside the sweat volume, and then that front realizes that it's wrong and self-corrects and backtracks, and we don't end up with any of that like fake local minima surface on the inside of the sweat volume. Yes, this is like really interesting. I refer you to the paper or to later to talk about this, but that's kind of the most interesting part of our contribution, but it's a bit harder to visualize, so I decided to skip it.
Sure.
Great. Okay. So
I also have a quick question, if that's all right.
Go ahead. Yeah.
Hi. You may get to this later, but how does your algorithm compare to that used by, say, like Bertini's homotopy continuation? Like in that case, you're trying to compute like the zero locus of a set like this, but then you could maybe output at every step of the algorithm, like what it currently thinks the answer is.
So we tried to draw, I guess not a comparison, like an analogy to those like traditional continuation algorithm works. Honestly, we couldn't really figure out how to put our algorithm, which we like intuitively interpreted as a continuation algorithm, because we're like tracing a zero level set. So that like feels like exactly what continuations algorithms are for, but we couldn't like put it in the context of most of the numerical continuation existing work. So we kind of gave up on that basically, because we feel like there isn't really like in most continuation algorithms where you're like, you have a function that you don't know, like an equation that you don't know how to solve, and you like add something to that equation that you then do know how to solve, and then sort of trace that zero level set to get closer to the solution of the first one. That's like, we couldn't put what we're doing, which we like intuitively call the continuation algorithm, in that context. So I guess my answer is, I don't know. We can probably go into more depth later. I'm going to assume that's okay and just keep going. Yeah, okay, I'll keep going. I'm going to take that as a yes. I think your connection bugged out a little bit, but I'm going to keep going. Okay, so we have this algorithm. We are tracing each boundary component by keeping track of these, where the global minima are, and we evaluate f by using gradient descent, using that information about the neighbor's global minima. So we do that efficiently. And of course, those earlier works that I was talking about not only help us find those grid cells, but also those global minima T star values. So the oracle is still valid here. Now, as a side note, you might be thinking that the reasoning that I made before about propagating things in space is very similar to the reasoning I made now about propagating the time parameter. And the fact that I could just turn one into the other by just adding a few words into this algorithm makes it feel like they're not exactly the same, but it's kind of like they rhyme. And that's not an accident. It's because our whole algorithm can be seen as a continuation algorithm on space-time. So if we take the 3D space that's made by time and space in this case, then so time on the plane, we can see that we're like tracing 1D, so a codimension 2 surface on the n+1D space. And this is a bit complicated, and it gets extremely complicated in 3D when we do sweeps of 3D surfaces, because that's when we'd be tracing a 2D surface on 4D space. So I didn't want to get into how you can visualize our algorithm like this, but you can also take a look at our paper where we introduce it precisely like this. Okay, so finally, the output of our algorithm, as we described it, is a set of grid points and a set of values of f. But we can just as easily take a look at all the interesting edges that we highlighted, do some line search in them to find the points where the surface intersects them, and then put them together to get a polyline representation of the swept volume surface. So we can add this to the algorithm as an optional final step if we just happen to want an explicit representation of the swept volume. And I wrote surface reconstruction here because, of course, what we want to do in the end is do all of this in 3D, right? Not just for a 2D simple disk. And everything I said carries over to 3D immediately. The grid cells are now cubic instead of square. And the surface reconstruction, we can do it with marching cubes or any grid to surface algorithm that we have in the geometry processing toolbox. In the examples I'll show, we'll use dual contouring, which is a very an improved, more modern version of marching cubes, but we could just as well use marching cubes. Okay, cool. So this is our complete algorithm. It took us a while to get here, but if you look at just 3 steps, it actually doesn't sound as complicated, right? There aren't these intersection resolving or pruning steps that could be complicated. There aren't any robustness challenges that become obvious that we could see with the previous work. So it's promising. So the next question is, how good is it, right? And there are several ways in which we can measure whether it's good or not. One is, well, remember back at the talk where there were these very restricted algorithms that only worked on some specific set of input meshes or a specific set of trajectories? Well, we can perfectly replicate even their flagship teaser results, while at the same time imposing none of those restrictions. So we can have other inputs, other trajectories that aren't restricted. So the only algorithm that is similar to ours in generality is the stamping algorithm that we saw before, which we were a bit disappointed that despite being naive, it was kind of like the state of the art for interactive applications, for some interactive applications. So how do we compare to it? Well, in this representative example, we see that the stamping would be catastrophic, creating topological noise and not being able to replicate even the zones that are swept by the thing components, especially the zones that are swept by the thing components. And there's also like some noise in the normal direction that you can see from the stamps themselves, right? Even if we attempted to improve the stamping by adding a mixture of continuous and discrete minimization, this is kind of like a stamping 2.0 that we added just to give it more of a fair shot in the paper. Even that does not work. And you can probably expect this. Our algorithm perfectly replicates the swept volume. And it doesn't matter that it's a thing component or anything like that. And at the same time, it's significantly faster. So we're better, faster than stamping, and we can replicate the results of much more restricted methods. Finally, there's one really nice feature of our algorithm that I haven't even told you about yet. I'm very excited to tell you about it. If you think about it, the only part of our algorithm that involves computing f is this step here. And we did it by gradient descent and all of that. In everything we said today, we assumed that f had this form. So it described a swept volume, right? But just as we considered this, we could have considered combine the swept volume with a CSG operation, like this other function, which takes the minimum of 2 swept volumes. So their union, right? And with our sign convention, this is the union. Or we could take the maximum, which would be their intersection, right? Or we could take this CSG operation, which is just the subtraction of an existing implicit shape minus a swept volume. And we could plug any of these into F and into the algorithm as F, and everything we just said would work just the same. The global minima that we are tracing would be the global minima of the CSG operation, not of the swept volume, but everything would work. And let's spend just a little bit of time understanding how cool this is. So, like we saw, if our F described a swept volume, this minimum, then our algorithm basically traced the boundary components of the swept volume. But what happens if what I want to compute is not the whole swept volume, but just the subtraction of blue rectangle minus swept volume? Then there's obviously no need to compute the whole swept volume, right? There's no need to compute the parts of the swept volume that are very far from the blue rectangle, because we're just doing that subtraction. So the output will be contained in the blue rectangle. Now, since we can give to our algorithm this new F, that means the subtraction, then our algorithm can trace this output of the CSG directly without the need to compute all of the swept volume, right? So this is output sensitive in complexity. So for example, say we want to compute the subtraction of a mountain minus the path of an object that goes through the mountain. Since we can incorporate CSG operations into our algorithm, then we can concentrate the queries that in the regions that really matter for the CSG output, right? Not waste time perfectly reconstructing the swept volume very far away from the output that we are going to get in the end. And we can get this output, which is output sensitive in runtime. We didn't need to compute the whole swept volume. Or we can check if a path and a rock intersect without the need to compute the swept volume of the whole trajectory, which when being persecuted by the forces of evil, every second counts. So this is some really nice and unique feature of our algorithm that I really like to showcase. But my favorite one is generality, because it's what most of the related work ends up being frustrating in. Our algorithm is extremely general, since it can work on any rigid trajectory and any input which accepts an implicit representation. So I want to end this talk by guiding you through some results that I think exemplify this generality. So for example, something we can do is we can find a distance from any point in space to a 2D polygonal curve like this one, which means that we can use our algorithm to compute the swept volume or the swept surface of a 2D curve. There are also shapes that have analytic implicit representations, and they can natively be incorporated into our algorithm. For example, a torus. We can transition between an L2 torus, which is a torus with a cylindrical and circular cross sections, and an L1 torus, which is like a torus but with square cross sections. We can transition between these two to obtain a ceramic vase. There's something that has made implicit representations very fashionable in the past few years is machine learning, right? So for example, here we directly sweep a neural network representation of a chair as obtained by Davis et al. And without need for any conversion, just by running their code to get the implicit function values, we obtain its swept volume. Of course, no matter what the machine learning people want to say, the most common shape representation is still a triangle mesh. Since we can compute signed distances from any point in space to a triangle mesh, we can also recover their swept volume with our algorithm. A union of triangle meshes can also be swept, even if they have independent trajectories, since that's just the union of swept volumes, which we can do because of the integration of CSG operations to get something like this. Now, our algorithm is so general, we can even do things that don't have a clear definition, like sweeping a point cloud. So thanks to the generalized winding number by Beryl et al., we can assign the distances to a point cloud. So our algorithm can do even that, which is sweep a point cloud around and compute its swept volume, whatever that means. This massive generality of our algorithm means that we can use it for any of the traditional swept volume application realms, like 3D modeling that we saw in the pumpkin carving example. We can use it for path planning, not only for resistance chase spaceships, but also for the more mundane autonomous cars, like where we can, for example, pre-test a parking maneuver to see if it intersects with any obstacle by computing its volume. We can use it for artistic applications. So for example, this pendulum's swept volume as it swings can be computed to get something like this. Then we can deduct it from the pink shape to create a satisfying animation. Now, our algorithm can even be used to do social commentary about the effects of capitalism. This is my first time giving a talk about this in the US, so I had to include this one. And even to check if we're dreaming or not by spinning a spin top and computing its swept volume. Now, I'd like to end by thanking all our academic and industrial sponsors, as well as everyone in the DGP lab in the University of Toronto, and most importantly, my two co-authors, Noah Meigerman from Adobe Research and Alex Jacobson from the University of Toronto and Adobe Research. Thank you very much for watching. I'm happy to elaborate on some of the questions now.
Thanks a lot for the great talk. Yeah.
Thank you for having me.
More questions from the audience?
I had a quick question.
Yeah.
So one thing I wasn't entirely clear on, you follow the actual boundary of the overall swept shape. So where you have sort of the self-intersecting disk being swept, you don't follow the boundaries that are subsumed by the self-intersection.
Right. Okay. Yeah, this. So the worst case scenario of our algorithm follows also the surfaces that are subdued, like you said. And then it eventually realizes that those surfaces are wrong, and it backtracks and corrects them. And our output, while having tracked those surfaces, does not contain those surfaces. Does that answer the question?
Okay, so it doesn't intentionally do that, but it might go in the wrong direction.
It might go temporarily in the wrong direction. Yeah.
Right. Yeah. I'm just with Justin as far as sort of, it seems like you could have a self-intersection that sort of happens and then goes away, leading to a second local minimum that briefly becomes global, then stops being global again, and you sort of never learn about it.
Right. Okay. So maybe like one thing that I also didn't get into is that we don't just start from one grid cell, right? In practice, what we do is we use these previous works that tell us how to generate candidate points, and we generate 100 grid cells or 1,000 grid cells. And if one of those is wrong, we just abort it immediately because we figure out that it has like all of the vertices that are inside, and we just forget about it, right? So seeding very aggressively, it doesn't make our complexity worse because we may just have more fronts that are covering the swept volume. They meet each other, they say hi, and they stop, right? That doesn't increase our complexity, but we could add more seeds theoretically to ensure that we're not missing any possible global minimum that happens at any point in time.
Okay, cool. Thanks.
Yeah, I see that I have a lot of questions about this. So I'm wondering if maybe there is some way I could explain this better in further iterations of this talk, because I find out that it's like actually one of the most interesting parts of the algorithm.
I had a question about the differentiability of your entire pipeline. I mean, sort of starting with your initial motivation, if the spaceship realizes that it will crash into the rock, can you automatically like perturb the trajectory to correct for that?
I don't think so, honestly. I don't know that we could, because I'm like not used to thinking of it in this way. But I don't think we could like immediately do that. Maybe there's a way, but like the fact that we have like this like sparse grid representation, right? Like eventually you move from one grid cell to the next and we just don't have any information in those grid cells. So we would like somehow need to like the output as you like move it would change the sparsity, right? So it would be really hard to think of that. I don't want to say no definitively, but yeah, I mean, I guess the idea is that the spaceship would have some internal thing that optimizes the trajectory to get through the rock, and then it would check that. Like in practice, I guess, like, you know, in practice, if the spaceship wanted to do like this, like funny example that I did at the beginning, it would like check for collisions with some convex hull much faster, right? And that's probably what the spaceship would do in like the real world. But yeah, it's kind of like a proof of concept that, you know, Tesla can have a lot of these pre-computed and check against different strategies for parking, I guess.
I see. One more question. I was wondering if you could talk a bit about the discretization error for putting this onto grid cells or cube cells.
Yeah.
Is there significant error or, you know?
Well, so we have a line in the paper that I think is the perfect answer to this, which is like, unless you're dealing with parametric shapes and you're okay with like representing the ruled surfaces parametrically, every algorithm that, you know, outputs a triangle mesh as a swept volume is an approximation, because the swept volume is not piecewise flat, right? So everything is an approximation in this field. The only so what you have to aim for is that you can control the approximation error, right? Then you can't be surprised suddenly. And since we're reconstructing from a grid, we kind of like have an idea of how bad the error can be. We can also refine the grid if we don't like that. And, you know, the cool thing about our algorithm is that it's quadratic in grid size, not cubic. So refining it wouldn't be as expensive as with other volumetric algorithms. But, you know, we have the same, if you interpret our pipeline as being like mesh to mesh, we have that final reconstruction step that has an error. We, in the context that we're thinking about it, we see it as a fully implicit to implicit pipeline. So that has no error at all. Like the error is the tolerance of your gradient descent. That's the error. So yeah, I guess it depends on how you interpret it.
I see.
In that same optics, I was wondering if you've tried to, maybe it's a little bit too far, but I work in mostly graphics for fabrication. And when we think about CAD and you're sweeping some volume for some engineering application, typically the fits are very critical at the end of the day. So I saw there's that nice animation with the artistic part where you actually have the pendulum going inside of the shape. If you were to actually build that, like 3D print it, will it actually fit? Because I wonder what is the actual amount of how high resolution you need to actually do that compared to what in practice is actually done for CAD. Because in CAD, when you do your swept volumes for any simple things, the output you get is like instantaneous. You can't just wait 30 minutes for it. So I'm wondering if you did any form of analysis between the, and trying to compare with a more physical target in mind.
Yeah, I think that's a great point. So specifically in that example, we swept a level set. We didn't sweep the pendulum, but like positive dilation of the pendulum by an amount that's the grid size, so that we can assure that if we printed that, it would like the bound on the error from the surface reconstruction would is smaller than the offset that we're doing, so that you can certainly print that without any worry. I don't know how to definitively answer your question. I think that I think our algorithm can run, you can wait time, and then it's very high resolution for like artistic applications. I think if you're just doing it to like check, like for path validation or things like that, then you could run our algorithm at a lower resolution with like an offset or something, and that would be reasonably fast, I think.
Okay, yeah, my impression is that what becomes critical at that point is the knowledge you have of the problem, so that you can tune the accuracy you're running at.
Definitely. I think, yeah, like I said, like everything in this field is mostly an approximation. So the important thing is that you have some control over that approximation, so that you can choose how much you're willing to tolerate in exchange for time, depending on the application, right?
Thanks a
Can I
lot.
ask a stupid Google search question?
Sure.
Since you're here and I'm being lazy. Is there a connection between this universe and like max plus algebra? Like somehow extracting the surface through like it smells like infimal convolution to me, but I can't quite write down if I wanted unnecessarily fancy notation to describe what you were doing.
I guess like, I don't know how I would do this with unnecessarily fancy notation, but I understand your instinct. I just don't, it's not my instinct, but I think there's probably a relation. I don't know, honestly, like,
okay.
My attempts to put this in like some traditional math realms, in those like week of the deadline where you think, oh, my method is too simple, maybe I should add a few like fracture letters so that people think
you
this
need
is some, like
tropical algebra, right?
Exactly. So that week of the deadline when I tried that didn't result in anything, but that just may be a limitation of what I can do, not of the algorithm.
It seems to have worked out okay regardless. All right, cool. Thanks.
Yeah, I'm reading Catherine's, hopefully I pronounce your name properly, comment. I think.
Yeah, that's exactly kind of what I had in mind too.
Yeah.
Yeah, again, like so specific that it might not even be interesting at that point, but there's probably like a generalization that you can do.
Yeah, it just smells like the same set of buzzwords. I don't know.
Yeah.
Yeah, maybe, I was just thinking that I wanted to do a follow-up to this work but it would feel very incremental. So maybe I'll look into this to make it sound smarter.
I don't know. I mean, if you want the direction of tropical geometry, my understanding is that tropical geometers are like constantly looking for really good applications of this. And so I think they'd be thrilled with anything.
Okay, well, I'll definitely look into this. Thank you very much.
Yeah, our group was approached by somebody in that universe who is like trying to make max plus algebra work inside of a deep network, just to be able to kind of say that they did. And it was a fun excuse for me to learn about it a little bit.
So I actually spent like a summer at the Max Planck Institute with maybe, like somebody in that organization.
Cool.
Yeah.
I'll definitely read into this and report back if that makes sense.
Sounds good.
Yeah, and again, I mentioned this in the chat, but I would love to talk to you more about like the connection to Bertini and like whether you can actually make like a direct analogy to it.
Yeah, I think like my answer is still that I don't know. So I would love to like get back to you, like look it up and give you a smart answer, because all my attempts have failed so far. So
cool. Yeah, great. Thank you.
My pleasure.
Thanks a lot. Guess I'll close the session now, and have a nice day.
You too. Thank you for having me.
Bye all.
And great talk. Thanks for joining us.